Hello, it's 1 o'clock and I'm waiting to see if anybody shows up to our virtual class. All right, I'm gonna stop recording while I wait.
One question is for our exam, um, I know it's the 27th. Are we able to take it? It has to be taken within that whole day, within
Right,
that whole time frame. So
right,
you get to choose whatever time in that day you could take it.
correct, correct.
Okay.
So I'm gonna set it up from like, I don't know, like 7 in the morning on Saturday until like 12 at night, 11:59 at night.
Cause yeah, I'm moving. Make sure my internet was ready, but if it's not, I'll just use my hotspot. Um, so I
Okay.
have a backup just in
Yes.
case.
Yeah, yeah.
Um,
No, it's whenever you want. It's going to be open all day. You can only take it once. So, yeah, make sure that internet is stable, all of that, because it'll
okay,
help you out, obviously.
right,
Um, that's a big problem.
right. Another question I wrote them down.
Are you moving to, well, we're recording. I'm not going to ask anything personal. All right. I'm glad you're
Sorry. Oh. Oh yeah. Also for the test, the tables that we're gonna be provided. Do we print them out and have them for the test? Is that how it's
Yes,
supposed to?
I'm glad you asked that because I think let me write that down and I'm going to send an announcement so that people are clear.
Okay.
Yeah, you can bring the equation sheet and the constant sheet. That's it.
Okay. Okay.
So you'll have to show that. Here's my equation sheet. Here's my constant sheet. I should have put that in the rules. I forgot. But okay, yeah. Send announcement about sheets and on test. Okay. And since you did ask about that, there is and I guess I'll send an announcement about that too. There are two conversions. I mean, typically when I'm in a face-to-face class, I say them over and over again, but since this is an online, if I don't see you, I forget.
Right.
So, there are two conversions that you need to be familiar with that are not on the equation sheet. The first one is the conversion that converts from metric units, so meter, centimeter, whatever, to English units. So it goes 1 centimeter cubed is equal to 1 milliliter.
Okay.
Actually, I said the backwards thing. There is one that goes from metric to English, and that's not the one. But that's the other one that you need to know. That conversion that I just gave you takes you from length to volume. And that's the
Okay.
other one that you need to know. So from 1 centimeter cubed, which is a length, because it's meter, is equal to 1 milliliter, which is a volume. So you need to know that one because that one's not on your sheet, and I tend to do problems that you need that. Especially problems that deal with
Okay.
like cube units. Definitely, I put that, like you have to get from a metric, from a length to a volume. That's what you're going to have to use. So 1 centimeter cubed is equal to 1 milliliter. The other one is the one that actually takes you from English to metric, and that is 1 inch is equal to 2.54 centimeters. So that takes you from English units to metric units. And that was really important because it actually, if you remember the quiz, the first quiz, maybe, I'm not sure, but I think the first quiz had a question, which I think that's why when the first time you came, you gave me those questions about gallons or yards or miles or whatever. Yeah, so a question like that takes you, I think, asked you to go from yards cubed to miles. So that one, you need, since it's a cube unit, you're going to need to use that 1 centimeter cube going to milliliter.
Right.
But something like that, like going from yards not cubed, but yards to meters, you're going to need the 1 inch is equal to 2.54 centimeters.
Right.
So those two you need to know,
Okay.
memorize, not write on the equation sheet. You just need to know them.
Okay. And also for limiting reagent, I know when we're like trying to find the excess reagent, you have to first be able to find the excess reagent, and then once you find the excess reagent, you subtract it from the because they provide you with two of the different.
I know where you're going because every single student does the same thing every semester. And I think what you're trying to ask, can't you subtract it from the beginning stuff that they give you once you find the excess reagent? Can't you just subtract? No, absolutely not.
Because I was looking, because I didn't do the subtraction, but I just found the excess reagent, and then then I had to do another thing to then subtract it from. But then when I saw the excess reagent and the number that they gave me in the beginning, and I subtracted it, it gave me the same number as.
And that might be a coincidence, but what you're asking me is once you find the excess reagent, right? So now you know which one was not used up. So that's the one. So once you found that, what you're saying is you took the answer from the limiting reagent, the answer, and then subtracted from the excess to see how much excess was left over. And that's incorrect because let's do a problem so I can show you.
Because I was saying because for one of the problems, it was like in one process, 124 grams of aluminum are reacted with 601 grams of iron 3 oxide. Calculate the mass in grams of aluminum oxide it formed. And so I tried to find the limiting reagent.
So who was the limiting reagent? Who was the limiting reagent in that problem?
The aluminum.
The aluminum, how much did the aluminum make? How much iron, what was the product again? Sorry.
It was 124 grams of aluminum reacted with 601 grams of iron.
No, I know. But what was the product of the reaction?
Oh, 2 aluminum plus iron.
Uh-oh, your internet. Say it again. Sorry. No, I don't want to know the reaction. I just want to know what the product was. What's the product of the reaction?
Oh yeah. So the formula that they gave me.
Yeah, just the product though.
Oh, okay. Aluminum oxide, I believe.
So what is the formula?
Al2O3.
Al2O3. Okay, so yes, that is aluminum oxide. So you said which one was the limiting reagent? Aluminum, you said?
Yes.
How much aluminum oxide was made from aluminum?
234 grams.
234 grams. And then what was the other reagent? Iron oxide, I think you said.
It was iron.
It's just iron. So you just have aluminum and iron. Go ahead.
Oh, no, wait. So on the product side, you're asking what was the...
No. Okay, reagents are on the left.
Yeah, correct. And then the products are on the right. Yeah.
Correct. So one of the reagents is aluminum by itself, right? What's the other reagent?
Oh, it's 383 grams.
Who is it?
Aluminum. This was with the iron oxide.
There you go. Iron oxide. And is it iron 2 oxide, iron 3 oxide? What is it?
Oxide.
I'm sorry,
iron 3 oxide.
3. Okay. Okay. So so you said that aluminum was the limiting reagent because you only got 234 grams of aluminum oxide, correct? Okay, so that means that the excess reagent is iron oxide.
Yes.
Okay, so now to find how much excess reagent is left over, was that the question that you had?
No, I know how to find it, but I was just wondering if you could, because I saw that if I subtracted 601 grams of iron oxide, which is what they gave me in the beginning, by 303 grams of the aluminum oxide that is left over, the excess reagent from the iron oxide, it will give me the same number as starting with the limiting reagent to find the excess reagent.
Tell me again one more time slowly what you did. You started out with 601 iron oxide. You
Right.
found out that iron oxide makes 303, right?
383.
383, so it made 383 of aluminum oxide.
Yes. Yes.
So that means that's the excess. Great. So to find how much excess was left over, you took out 601 minus 383.
Yes, but I didn't do that at first.
Don't do that because that is incorrect.
Yeah, because at first I did what you said in the video. You start with the limiting reagent and then multiply it and do the mole thing.
Right.
But once I got that answer, when then I subtracted the 601 by the answer I got from that equation, I got 234 iron oxide.
Okay, that's correct.
And when I did the 300, yeah. But then when I saw that there was 300 and when I got the 383 grams of iron, not iron oxide, aluminum oxide excess reagent. Oh wait, I can't subtract that from.
Yeah, no, okay, so the main thing is that you can't, okay, students every semester, because this is a big thing, right? And what they want to do is everyone understand or kind of understands how to get limiting reagents. They understand how to figure out which one's the excess. That's pretty easy. They can even understand how to do theoretical yield because that's basically going from the limiting to the product, right? That's my theoretical yield because that's the dude that limits the reaction. Everyone understands that. But then if I ask them how to get the excess reagent, what they want to do is either they want to go from the excess reagent equation, right? So that's wrong because you never make excess reagent. You never make 383
Right.
grams of aluminum oxide. So you can't take that away from 601 from the beginning because you never make it.
Right.
So that's always what they want to do. Or they simply want to take how much they got of aluminum oxide. So you said you got, how much did you get of aluminum oxide? 234 from aluminum?
Yes.
Right. So they say, okay, so since we made 234, why don't we just subtract 601 from 234? Because 601 is how much I started of iron oxide, right? So, and they're like, okay, so if that's how much we made of the product, why can't we just subtract the product from the excess? Because it's not the same thing. And that's the main reason.
Is the aluminum oxide, not iron.
Right. You can't subtract 234 grams of aluminum oxide from iron oxide. They're apples and oranges. So that's the reason you can't do it. So the reason you have to start from the limiting is because, first of all, that's how much you make. So that's it. That's all you got to work with. And you take that back to and convert it to the person that you're looking for, right? Which is iron oxide. That'll give you a number. That number is how much you use of the iron oxide. So therefore, now you can take the beginning, 601, minus how much you used of iron oxide, and that'll give you the excess that's left over.
Okay. Yeah, now I get it. Thanks.
Good.
And can you also, so I understand chapter 4, but it's kind of confusing.
It's not confusing. I think it's just that it's a lot. It really is.
Yeah.
If you had more time to go through it, it wouldn't be as confusing. It's not confusing. It's very to the point, but it's just a lot. It's a lot of stuff. So what in particular are you confused about?
I'm mainly confused about like how to break the aqueous down. So when you're trying to break it down, so you can find the iron, ionic, what is it?
Equation? Are you talking about
The
precipitation
net
equation?
ionic equation. Yeah.
Okay. So first of all, precipitation equations are like one of the easiest things. If you can get this limiting excess thing, then you've done the hardest thing. So precipitation reactions are super easy. All right. The precipitation reactions are also called double displacement reactions. So are you having trouble when you do those problems? Are you having trouble making the making the products correctly? Or what, are you just having problem splitting the ionic portions correctly?
I think I'm having trouble splitting the ionic portions correctly because
Okay.
I'm not sure. I think it's because I'm not so sure. I need to go back and study the periodic table for
Uh-huh.
charges and stuff.
Yep,
Yeah.
that was going to be my thing. I was just going to tell you, if you don't know how to split them up, it's because you don't know how to read the periodic table. And it's because, I mean, if you knew how to read the periodic table, it would be easy. It's like super
Right.
easy because you know what charge what makes always. So for example, if you have I don't know, let me share with you so I can at least do some examples. Share. Okay. So do you remember one that you had problems with or no? Just by the way, look, this is my work from my general chemistry 2 class. So you're pretty lucky that you're only doing. Anyway, do you have one like one off the top of your head that you remember?
I have,
Ooh, you broke up.
it says write the ionic. Oh, do you hear me?
Now I do, yeah. Hello? Yes, I do. I hear you.
Okay. It,
Go ahead, one more time.
it says write the net ionic equation for the reaction that occurs when aqueous iron 3 sulfate is added to aqueous sodium sulfide to produce solid iron 3 sulfide and
Whoa, that's too fast, Cecilia. Hold on a second. I'm only on the first one.
Sorry.
Sulfate reacts with what?
Okay. Okay, so it was aqueous iron 3 sulfate is added to aqueous sodium sulfide.
Okay, stop right there. Sodium.
Hello?
Yeah, stop right there.
Okay.
Okay, so from here, I don't need anything else because I know I can make products. Okay. Let me just see.
Dr. Tournay, you're breaking up.
Oh, hello? Hello? Hold on. How about I chat? Chat. Chat. Do you see the chat?
Yes.
Okay. Why don't I can hear you? Can you hear me now? Can you hear me?
Yes, I hear you now.
Okay, you can hear me now?
Yeah.
Okay. What I was saying is that this problem gives you products, or it does not give you products? Can't hear me. Does the problem give you products?
Yes, the problem gives me products.
Okay. You don't, oops, don't need. So you have a NaSO4. Chat. Okay. NaSO4 and Fe, and it's iron 3, so Fe2S3. Is that correct?
Yes.
Okay. Find if they're aqueous. Do you know how to find if they're aqueous?
It already states that they're aqueous.
It already states that they're aqueous?
Yes.
Okay, so everything in this equation is aqueous?
No, except for Fe2S3.
S3. Okay, so do you know how to find if they didn't tell you? Do you know how to find if they didn't tell you? Do you know how to figure out if they're aqueous or not? Okay. You use the solubility table.
Okay.
Okay. In your book. Okay. You will be given a solubility table, in your exam. So you need to know how to read it, Got it?
Yes.
Okay.
On the exam, are we gonna have to be able to know if one equation is aqueous and to figure out the aqueous and?
Yep, you are. So that table, can you hear me?
Yeah, I hear you now.
That table is not that easy to read. So you just look at it and do a couple problems and make sure, because in the back of the chapter, there are several problems that just ask, is this aqueous? Is this not aqueous? So you can practice using the table. Okay. So since this is solid, this is aqueous, then it becomes easy, because really all you got to do is split things apart. The trick to knowing how to split things apart is you have to know how to read the periodic table, and that's number one. Number two is you have to know your polyatomic ions, because you have to be able to recognize your polyatomic ions, because your polyatomic ions don't split up, they stay together, right? So here, when I do my ionic equation, I know for a fact that SO4, sulfate, is going to stay together. So I have to split this up in a way that makes sense. So how is it going to split? It's going to split, I have, how many Fe's do you have in this equation at the beginning?
2.
Right, so I need to put 2 Fe with the charge of Fe. What is the charge of Fe?
-3.
Did you say negative?
I meant +3.
Yes, metals are not negative.
+3.
All right, so 2 Fe 3 plus. Why? Because look at the 3 right here, right? The 3, they uncross. I'm unstable. Can you hear me? Yeah, you can hear me? Can you hear me? Can you hear me?
Now I can.
Okay, so yeah, it's Fe plus 3 because you uncross the charges, right? So now what's the other half of that molecule? What do I need to write?
SO4 2 minus.
Okay, but you only have one SO4?
Oh, 3.
Yes, you have to do that, because if you don't put how many you have, then it won't work out at the end. You have to specifically do everything, like you have to put how many SO4, how many compounds, how many ions you have of it, because later you're going to cancel stuff and it won't cancel if you don't do it right. So that's that equation, that compound. What's the other one? The other one would be 2 Na plus,
Na.
but plus, right? Plus S2 minus. Okay. Going to aqueous, which would be 2 Na plus SO4 2 minus. Does that make sense? Okay. Plus this guy stays the same because it's a solid. It doesn't break up. So now you have all these things that you can cross out. For example, look at your Na. Na is on the right.
Dr. Tornado.
Yeah. Say again.
I just had a quick question.
Mm-hmm.
So when you do the charges, when you break them down and you put the charges down, the charges are always from the other compound connected to it on the bottom. So like iron 3 sulfate, it would be iron plus 3 because there's 3 of the sulfate.
That in my video, that's how back in chapter 2, that's how I showed you how to make ionic compounds, right? So you uncross the charges is an easy way to remember. Okay. But to do that, you have to be really comfortable with knowing the polyatomic charges as well. So for example, NaNO3, right? That's sodium nitrate. Here, what is the charge of Na?
Na is -1. I meant 1, sorry. I keep saying negative. +1.
+1. So Na would be +1 and NO3, it would be -1, right? Because you have to understand that this whole thing is a unit, which is a polyatomic anion being a negative charge. But if you remember the videos, it's all, why does that work? Why does the uncrossing work? It's because it's a math problem. All it is a math problem. So for example, if I have, let's see, what can I do? Carbonate, how about sodium carbonate, right? Sodium carbonate. If I want to know what the charge of carbonate is, and let's say I didn't know, I could figure it out by looking at this problem and setting it up to a math equation. Do you know what I mean by that? Do you know what I mean by setting it up to a math equation?
By doing the cross method?
Yeah, like if I, let's say for example, if I didn't know what the charge of carbonate was, let's say I didn't know. I know that you can look at it right now and say, oh, just uncross it. But let's say I didn't know. The way you could find out is by setting this problem like a math problem. So you would equal it, like make a problem. The problem is you would equal it to whatever the charge of the molecule is. Did you hear that or no? Did you hear me?
Yes, whatever the charge the molecule is.
Right, so since sodium carbonate has no charge, right, the molecule has no charge, I'll put it equal to 0, okay? And I'm trying to find what the charge of carbonate is. So I would say, okay, that is my X. So therefore, I can figure out what X is if I know what the other one is. You should know what sodium is because that's always +1 because it's always on, it's in the first column. First columns are always +1, always. So I have 2 of them, right? 2 sodiums, and each of them are +1. So therefore, if I solve for X, X is going to be equal to -2, which is why carbonate is equal to -2. So that process you can do if you didn't know something. You see what I'm saying? If you didn't know a particular charge of an atom, of an ion, you can set it up like a math problem. So that maybe will help you when you do these things. If you put them together or take them apart, you can kind of play with that. But yes, in general, ionic compounds only come together one way. So that's why making it equal to a math problem, it will work because there's no choice, right? Ionic compounds have to come together to neutralize their charge. So if they neutralize their charge, you can set it up to a math problem. So going back to this, you can cancel the 2 NAs on both sides, and you can cancel, oh, we didn't balance this equation. That's a big problem. So right there, look, there's 3 SO4s on the left, and there's only 1 SO4 on the right. So therefore, that wouldn't work. So you can't cancel it. So that means that we need to properly balance it. Oof, my bad. So you need, if there's 3 SO4s here, you have to have 3 SO4s here, which means this makes 6 Na pluses, which means this has to be a 3, which means this changes to 6 and this changes to 6. Okay, that is very important that you do that. So in that case, this would be 3 SO4, and now this cancels. Okay, and the only thing that you're left with is the easy part, right? This is this and this will make your solid. That is the whole point of a precipitation reaction. The precipitation reaction only, basically, the only people that are actually reacting are the people who are making the solid. Everybody else, I think I said it in the video, everybody else is just going to the, basically, what do I say in class? I say they're like designated drivers to a party, right? They can't drink, they can't really do anything. They just kind of sit there and take the people that are going to party, they take them to the party. So that's what these guys are. These guys, all of these guys are the designated drivers. They take them to the party. And then these guys are the guys that party because they're the ones that make the solid. Okay. So
You're saying like
spectator ions, right? They just spectate. They're just there watching the party, people having fun, but they can't do anything. So that's why they cancel out. So it's really easy. Precipitation reactions are really easy. As soon as you know who the solid is, you know who's going to be at the end of the problem, right? So if I, at the beginning, when you said iron 3 sulfide was the solid, I already knew, okay, so that means that iron and sulfur are going to be at the end, and everybody else should cancel. Does that make sense? Yeah.
All right.
So the trick to knowing how to break them apart is you got to know your polyatomics, and you got to know how to read the periodic table. I will say, know the ones that never change. What do I mean by that? Your first 2 columns of your periodic table, yeah, the first 2 columns never change. They are always +1 and +2. They
so
never,
are the metals that change are the transition metals that those change?
well, there are non-metals that can change depending on who they are attracted to, but for the most part, transition metals are the ones that transition. Yes. For this class, yes, that's what you're looking for. Transition metals are freaky, right? They're very hard, they're difficult. So you're not going to know them. So therefore, you need to know the other thing that's connected to it to be able to find out what the transition metal is. Does that make sense?
Yes.
Yeah. So for example, potassium permanganate. So do you know what the permanganate charge is?
No.
But you do, because this is an ionic compound, right?
But I know what the potassium charge.
What is the potassium charges? What is it?
On the periodic table.
Yeah, look, get a periodic table, don't guess.
So potassium is +1.
So what is permanganate?
-1.
Exactly. Why? Because in your head, you just basically made a little math problem. It's equal to 0, I need X, I have 1K, so that means X is equal to -1. It's basically how you do it, right? So to find stuff that you don't know, you got to know the other ones. But you just really have to know the ones that never change. For example, are the first column, the alkali metals, and the alkali earth metals. Those are always +1, and the other ones are always +2, always. And those will help you when you're trying to figure out stuff. Another thing that never changes is fluorine. Fluorine is always -1 because non-metals, like I said, could change. But fluorine is always -1. And another thing that that would help you in these precipitation reaction is knowing that nitrate, NO3-, is always soluble. So that dude, if you have a nitrate in your compounds, in any of the compounds, it's always going to be aqueous. Always. So don't waste your time looking in the chart. Oh wait, it's a nitrate. Is it aqueous? Yes, nitrates are always aqueous. Always. They always dissolve. So that'll save you a little bit of time when you're trying to do the problems. Knowing the ones that are always aqueous are nitrates, the first two columns, K plus, and you know, the alkali and alkali metals, alkali earth metals, those are always aqueous. If you look at the chart, you'll see alkali metals always aqueous. Alkali earth metals, but there's small exceptions, but they're usually aqueous, and nitrates are also aqueous. Does that make sense? I'm breaking up. I'm breaking up. So
Yeah.
alkali and alkali earth metals are always soluble as well as nitrates.
Okay.
All right, so hold on, let me stop.
I think I can hear you now.
Okay, maybe it's when I share the screen, it's not as easy. But anyway, did that make sense? I'm breaking up.
Yes, it does. Yeah.
Oh, okay. Do you have any other questions?
No. Therefore, I think. Well, I know well. Chapter 3, I'm pretty good at. I did a lot of problems yesterday, so I got in the hang of that. So I think today I'm just going to continue doing problems for chapter 4.
Okay. Hold on. Let me show you. So this is the on page, what edition do you have of the book? 11?
I have, what is this?
Is it the blue one?
It's the red one.
Oh, the red one? I don't know what the red one is.
It says, well, I don't know. It's a rental. It says Chang and Goldson 12E. Oh no.
Okay,
It's
that's
a
the
PDF.
12th edition. That's a 12th edition.
Okay.
So you have the newer one. I have the old one. On the one that I have, the solubility table. Oh, hold on. Oh, hold on. There you go. Is that.
Okay.
It's on page 122. And what I want you to note is that the solubility table in your exam is not going to look exactly like this. It's gonna have everything except the examples of what alkali metals are, right? So it's just gonna say compounds containing alkali metals.
Worksheets already on.
Say again, sorry.
You have the worksheets already on Blackboard to print.
Not of this. Not of the solubility table.
Okay.
Okay, but what you could do is you could go to the old exams, and the old exams that are posted, they'll show you an example of what the solubility table will look like. Because I provide it for you, I give it to you.
Okay.
And actually, you know what, Cecilia? Now that I'm thinking about it, I think I am going to provide the sheets for you. The equation sheet and the constant sheet, so you don't have to print them, because some people might not be able to print them. So I'm just gonna have it on the exam. So what I did before in last semester was that those would be questions, like number 1, you'll see the equation sheet. Number 2, the constant sheet, but you don't have to answer anything. They're just there so you can scroll up and down. But
Right.
so you can use it. So you don't have to print them.
And how, so are we just, for the exam, are we just writing the answers? Because I know it's kind of troubling writing the answers when we're taking the pre-assessment and post-assessment, trying to type them. So are we writing the answers on the thing?
Nope.
Or
All you have to say, all you have to say on on the exam itself, all you have to say is answer on page whatever of your pages. So like, let's say you have 3 pages that you're writing on, you have to number them and just put answer on page 2, answer on page 3, answer, and then everything is on your paperwork.
Okay.
So yeah, you don't have to answer anything unless it's a multiple choice. If it's a multiple choice, then you just pick whatever you want, which there probably won't be a multiple choice. Right. So yeah, I'm gonna send the announcement about the sheets and how you don't need them. And then I'm gonna also say about the constants, those two equations, conversions, that you need to know.
No.
The cubic centimeter cube to milliliter and inch to centimeter. Yeah. All right, what else? What other questions do you have?
That's it as of right now.
Okay, cool. I hope this helped.
Yes, it did. Thank you so much.
And
And also, I emailed you on the wrong address.
Yeah, the video, you mean? Yeah. And I don't know how long it's been like that. And no one has said anything. So I don't know. I hope that people figured out that it was the wrong video. I don't know. But thank you for letting me know. All right. Thank you. See ya.
No problem. Because wait, I saw it.
Yeah.
Later.
Bye.
Bye.